Yeah, so my name is Patrick. I'm a lead software engineer here on the group's data platform team at Klaviyo, and we're very fortunate to be able to host the ClickHouse Meetup. So thank you to ClickHouse, and thank you to you all for coming. Today, we'll be spending some time talking about how we've optimized time-based segment evaluation with ClickHouse. I'll start by providing a brief overview of what Klaviyo is and what the segmentation service looks like. Yeah, so Klaviyo is a CRM for B2C companies, and among many other things, Klaviyo allows our customers to segment their user profiles based on different criteria. So here on the left, there's an example of a user profile, Alice, with a bunch of events attached to her and some properties. And then on the right, a segment. These segments are made up of stanzas, and each stanza is made up of one or more criteria. The criteria are ORed together with a logical OR, and then the results of each stanza are ANDed together with a logical AND to compute a set of profiles that qualifies for a given segment. The segmentation service has three core processing modes. The first is initial segment creation. And so this is when someone creates a new segment or edits an existing segment in our UI, in our APIs. We'll compute an initial set of profiles that qualify for that segment. We'll also keep segments up to date over in real time as data comes in. And so we have orchestration systems for that. And then we also have a workflow that manages time-based periodic updates. And so this is adding or removing segment memberships as time elapses. It's not an event-driven workflow, but triggered by the elapsing of time. And this is what we're going to focus on today. Some background about our ClickHouse cluster. We have 192 hosts, and we use bi-level sharding, so we have two sharding keys. First, we'll shard by the company ID, which is a unique ID for each of our customers, and this allows us to isolate customers from each other. We'll then shard each layer 8 ways by the profile ID. And so we're effectively distributing all of a company's data across 8 shards, which allows us to query them in parallel. And then we have a replication factor of 3. And then we have multiple EBS volumes attached to each of these hosts. There's 4 core tables that we'll be touching on today. The first is the segment definitions local table. It's a replacing merge tree table that stores a copy of all of the segment definitions that we want to keep up to date. We store this in a table in ClickHouse so that we can then query it later on. The next 2 tables, events and traits, are data tables. Events local is relatively straightforward. It's an append-only log of events, ordered a time series log of events partitioned by month. Traits local is a little bit more interesting. It stores snapshots of profile data. We use a replacing merge tree table engine, and so as data about a profile changes, we'll insert fully new trait rows into the traits local table and then defer the compaction of that to ClickHouse asynchronously. But it stores attributes about a profile. So we'll store, for example, consent data here, we'll store predictive analytics data here, and then differentiate each class of data with a column that we call the source ID. And then we have this last table, the segment results log local table. And so a number of the queries that we evaluate will generate segment memberships and then write them to this table. And then we have separate components that will scan this and then process those segment memberships, sending them elsewhere. And so it's an insert into select styled query here. This is a high-level overview of the system. So in gray, we have some ingestion for traits and events that will perform batch inserts into the ClickHouse cluster. In blue, we have query orchestration, so an API where we'll create new segments, and then query executors. These are Python Kubernetes pods that are periodically executing queries against the ClickHouse cluster to generate segment memberships, for example, to keep them up to date as we receive new data and so on. And then in green, the result extraction pipeline. So this is scanning that result log local table that we were just touching on, extracting the segment memberships, persisting the up-to-date record of that in a transactional database, and then publishing a change stream. So with this context, we're going to dive into time-based periodic updates a little bit more. Here, I have an example of a segment, birthday date is today. And the set of memberships that would qualify for this segment is determined by the elapsing of time. For example, today will include people whose birthday is today, and then the day will elapse and we'll add new people and remove some. It's not an event-driven workflow, but based on time elapsing. Another example, opened email at least once between 3 and 5 days ago. Again, the memberships for this segment are determined by events, but they change as time elapses. And so when we first launched the segmentation service on ClickHouse, the solution we used for this was to keep these segments up to date was to effectively reevaluate them in their entirety on some regular cadence. And it worked reasonably well for some period of time. But as you can see here, the volume of segment memberships generated with that approach was very high. Around 60% of all of the segments at Klaviyo have these relative time filters in them. And so this is a graph showing the volume that the result extraction pipeline is processing, the number of memberships. And we'll peak at 53 million requests per second, which is pretty fast. This is across all of the 192 nodes, so that's the different colors there. We also noticed, though, that most of the segment memberships that were being generated were not terribly meaningful. They were effectively duplicates. So in this example, you can see that profile 1 qualified on the 19th, again on the 20th, and again on the 21st. So reevaluating all of the segments in full, we're generating a lot of duplicate memberships that we didn't have to do any further processing on. And so as we were thinking about how we could optimize this system, we realized that we could scope updates to specific time intervals, or rather to profiles that have data within these specific time intervals. So we'll add you to a birthday property is today segment if your birthday is today, and remove you if your birthday was tomorrow. Or in the example of the opened email between 3 and 5 days ago segment, we'll add you, or we might have to add you if you had opened an email 3 days ago, and we might have to remove you from the segment if you had opened an email 6 days ago, because that might be the only opened email event that you've performed. And so the core thesis here is that instead of updating segment memberships for every profile, we'll run a lightweight query against the events and trait tables to identify profiles with events or properties within specific time bounds, and then only update segment memberships for those profiles. It's relatively straightforward for events running this query because events are already time series aligned. The data is partitioned by month, and so you can run a relatively lightweight query to find profiles with events between certain time bounds. It's a lot harder for traits, though, because traits are not laid out by time. They're snapshots of profile data. And so we'd end up having to read all of the trait data for a company to compute a meaningful answer here, which would be a lot. Digging into that a little bit further, here's an example of a trait row. So this is a profile property. This is the type of data stored in the traits local table for profile 1. And this created at timestamp here is the key that we use in the replacing merge tree table, representing the version of this record. And so as a new record is inserted, it would have a greater created at timestamp. But then we represent the trait data with 3 columns. Property keys, which stores the key. Property vals stir, which stores the string representation of the value. And then property vals numeric, which stores the numeric representation of the value. And for dates, we'll store Unix timestamps. So that's the birthday 322808400. And so you'll notice that if we're trying to fetch the birthday property, we'll read these property key columns, but there's a lot of overhead coming into play here. Everything in red is data that you're reading off of disk, but that isn't meaningful. It's not meaningful for answering the question at hand. And so we started to think about different ways that we could represent this data on disk. And with that, we came up with this EAV table, EAV standing for Entity Attribute Value. So we created a separate table that has this property name included in the order by key. And with this table, we'll store 1 row per property. So you'll see the property name, the value stir, and the value float. And we'll populate that table using a ClickHouse materialized view. So whenever data is inserted into traits local, the materialized view will execute. It'll explode that row out into one row per property and then insert that into the EAV table so they're in sync. And now we can perform very targeted queries for that specific property. So put birthday in there because it's in the order by key. And so this is an example of what that looks like for the previous record. So we've talked about how we lay the data out on disk. Now let's talk about how we determine which profile ID, segment ID pairs need to be updated. We'll talk about the query. This is a high-level sketch of the query that we run, and there's a lot here, so we're going to break this down piece by piece. First, we define a common table expression called trait criteria, which is a record of all of the trait criteria that have one of these properties with a relative time filter. And so you'll notice that we're querying segment f's local, which is that ClickHouse table with all of the segment definitions that we care about. We'll then select the profile ID and segment ID from the traits EAV local table that we were just looking at, join it to the trait criteria, and then call out to this function that we've defined, datetime and window. We'll pass in the date property and then the filters. And this function will tell us whether the datetime value falls within these time bounds and would thus need to be updated. We'll filter the read to the EAV table to properties that are actually used in one of these segments, to properties that actually have a criteria with a relative time filter. And this is a bit more interesting. So since the EAV table is a replacing merge tree that would potentially have multiple versions of a record, we do some filtering so that we filter to the record in the EAV table that corresponds to the max created at timestamp in the traits local table. So effectively, instead of reading all of the EAV records, because they would get populated as new traits are inserted, we'll scope the read to the most up-to-date record. And you might ask, well, why don't you just aggregate the data in the EAV table by the version key and then use the latest version there? But this approach allows us to get around data deletions. So for example, if a property was deleted on a trait, if a property was deleted, we'd insert a new trait row without that property present. The materialized view would execute and insert rows into the EAV table. But because the property doesn't exist there, nothing would be inserted into the EAV table. And so we'd effectively be querying stale data and then generating more of these profile ID segment ID pairs than we would otherwise need to. And this is also rather interesting. So we realized that instead of aggregating the created at timestamp for every profile in the account when reading from traits local, we could scope that aggregation to profiles that actually have one of these properties or have had over at one point in time. And so I think the key lesson here was pushing down as many conditions as possible when reading data. And you'll notice that this SQL is effectively the same as the SQL shown at the top of the query. Again, we're selecting the profile ID from EAV, reading from the trait criteria table. So it's a little bit roundabout, but we saw really meaningful performance improvements when we were pushing down conditions into the subqueries to reduce the amount of data that we were reading. And so we've been talking about the logic, the lightweight filtering effectively to determine which profile ID segment ID pairs we update. But I wanted to touch on how this fits together with the larger orchestration system. So we run this query to determine the scope of the work, right? What profile segment ID pairs do we have to update? And then we'll publish that data or chunk that data up into a series of batches, publish the batches to a message queue, and then consume those batches and run a separate query that will actually go through the process of updating segment memberships. And we chose to structure it this way because it allows us to easily horizontally scale this approach. The lightweight query is very fast, but the actual process of updating the segment memberships is more intensive. And so by batching the work up front, we can fan it out to more consumers and run that at a higher parallelism. Yeah, so all of the things that we've been talking about today are the result of a lot of hard work from many, many people, many of whom are here today. Yeah, thank you for listening, and I'm happy to take any questions that you might have.
So this kind of came to me just randomly. Why do we have both a string and a numeric representation?
Yeah, it enables us to provide a richer set of querying functionality to our customers. There are some operators, we call them, that would best be served by the string representation of a value, whereas other operators would be better served with a numeric representation, for example. And then there's other representations there that we excluded for the sake of the talk, but basically providing more richness to the data to extend the query functionality that we expose to our customers.
Any specific reason why you chose ClickHouse?
Yeah, that's a good question. Yeah, any specific reasons why we chose ClickHouse in the first place? We had some in-house experience with it when we were re-architecting the segmentation service, and so that was a key driver, but we knew that it was very fast. The operations around it were very, there was a very compelling story there as well, and we knew that it could satisfy the use case, and so we explored a few different options and found this to be the best. Great, yeah, thank you all very much.